Hello, this is Elizabeth from the Academic Support Center at Raritan Valley Community College, and I have a brief lesson on logarithmic equations. So a logarithmic equation is when we have a log with a variable inside the logarithm, and we want to solve for that variable. There's two main ways that we solve these types of equations, and one of them is by evoking the definition of log, which is over here. Log base b of m equals c. That really means b to the c equals m. So we're asking b to the what power gives us m. Okay, we're going to use that. I have over here a couple of the other log rules that we've been over in other sections, but log base, the power rule, the product rule, and the quotient rule, and they're here for your reference. And we will actually use some of them in the examples I have today, but these are things that I'm assuming that you've seen before, okay? So the first way that we solve these logarithmic equations is by using this definition or rewriting it in exponential form. And I have an example of one of those that we can go through and take a look at. So if I have something that looks like 2 log base 3 of x plus 4, this is equal to log base 3 of 9 plus 2. Okay, so we want to get all of our log base 3 stuff together. So you'll notice we have a logarithmic with something within our exponent. So what I'd like to do is, you could look at this and say log base 3 of 9 is 2, and that's 4, and simplify it that way. But I'm going to go through just like using our log rules and combining things. So the first thing I want to do is I want to evoke our power rule. I'm going to put this 2 as an exponent up here. So I'm going to rewrite this as log base 3 of x plus 4 squared. So that's the product rule. Okay. So the next thing I want to do is I want to get all of my log stuff together. Okay, so this is a 9, and we could probably do that. But if it was x or if it was something else, we want to condense all of our log stuff together. So I'm going to subtract log base 3 of 9 from both sides. So this is log base 3 of x plus 4 squared minus log base 3 of 9 is equal to 2. Okay, now I can use my quotient rule in reverse to get this left hand of my side of my equation as a single logarithmic expression. So we have log base 3 of, this is x plus 4 squared divided by 9, because when we subtract, it's a division. All of this is equal to 2. Okay, so this is the first part, is that we want to isolate a single logarithmic expression. Now, this is something that's in a form where we can invoke this definition, where we can say that b to the c, so 3 to the 3 squared, is equal to, this was my m, it's equal to x plus 4 squared divided by 9. Well, 3 squared is 9, and then I can multiply both sides of the equation by 9. So we end up with 9 times 9. This is 81 is equal to x plus 4 times x plus 4. Okay, so 81 is equal to x squared plus 4x plus 4x plus 8x plus 16. And then we minus 81. So this is all algebra manipulation after we invoked our definition. But now we can say 0 is equal to x squared plus 8x. 16 minus 81, that's negative 65. And now we can factor this. Comes x multiplies to negative 65, adds to 8, that's plus 13 and minus 5. So x can equal negative 13, or x is equal to 5. Now, whenever we have a logarithmic equation, we always want to go back to the original equation and plug in our answer. We cannot take the log of a negative number. So if plugging any of these in to our original equation gives us a negative number, then it's not a valid answer. So we always want to go back and plug that in. So we plug negative 13 in here. We have log of x plus 4. Negative 13 plus 4 is negative 9. That will be a log of a negative number. So this is not a valid answer. If we plug in x equals 5, x equals 5 plus 4 is 9. And log base 3 of 9 is 2 times 2 is 4. And log base 3 of 9 is 2 plus 2 is 4. So 5 checks out. You can always go back and plug them in. And you definitely need to, regardless of if you have positive or negative answers. If this was x minus 4, then like an answer of 3 would still give you a negative number. Okay, so what we did here, just in review, we had an equation with an x or a variable of any sort inside of our log function. We wanted to solve for that x. So we simplified so that we had, we got to here, so that we had a log of something equals something. And then we can evoke our definition of logarithms to rewrite this. And then we simplify it using algebra. So we isolate our log, we use the definition, and then we simplify. Maybe that's worth writing out. 1, isolate. 2, use our definition. And then 3 is simplify. Okay. The other type of example that we can do, I'm just going to move this over here, is so that we can still see this information here, is we can do something where we have logs on both sides of our equation. And if we can get two simple logs equal to each other, then we can say that whatever inside that log is the same. So in other words, let me write this out and make more sense. We have log base b of m is equal to log base b of n. Logarithmic function is 1 to 1, so we can say m is equal to n. So that's what we're going to aim to do in this type of a question. So we have two logs on both sides, we set them equal. The thing that we're taking the log of should be the same. So this is just an example. We have log of x plus log of x plus 3 is equal to log of 10. Okay? So we want to solve for x, and x is inside the logarithmic function. So to go about doing that, we want logs on the same, a simple log equation on one side and a simple log equation on the other side. So we can combine these. We're going to use the product rule here. We have log of x plus 3. That we can condense down using the product rule is log of x times x plus 3. And this is equal to log of 10. So we have a log of something is equal to a log of something. So those two things should be the same. So we're going to evoke this one-to-one principle that we talked about up here. So we're going to say that this is x times x plus 3 is equal to 10. Because log of x plus 3, log of x times x plus 3 was equal to the log of 10. Therefore, they're the same. So this becomes x squared plus 3x. We're going to subtract 10 from both sides. Minus 10 is equal to 0. And now again, we can factor this. We're going to factor this is x plus 5 times x minus 2 is equal to 0. So x, if we set this equal to 0, x will be equal to 5. This half equal to 0, x will be equal to 2. This is negative 5 and 2. So we have to go back to this original equation. Again, we can't have the log of a negative number. If we plug negative 5 in here, this is log of negative 5. We can't do that. That's not part of our domain. That's not a valid answer. If we plug 2 in, we get log of 2 plus log of 2 plus 3, 5. That is valid. And if you go through the math, you can verify that answer. Okay? So that's pretty much the two ways that we can solve our logarithmic equations. In both cases, we want to simplify so that we have a simple log equation either on one side or two sides. If we can isolate the log on one side and then set that equal to something, we can use the definition and rewrite it in the exponential form and then do the algebra to solve it. If we have logs on both sides of the equation, we can get a simple logarithmic on each side and then set those two things that we're taking logs of equal to each other. And then again, it's algebraic manipulation. In all logarithmic equations, we always want to go back and plug our answers in to ensure that in the original equation that we aren't taking the log of a negative number. Okay. Again, this is Academic Support Center at Raritan Valley Community College, and we are here to help. If you have any questions, please feel free to reach out. We are online during the COVID-19 shutdown, and we will be, when everything goes back to normal, we'll be back on campus in person at the Academic Support Center. If you have any questions, please don't hesitate. Thank you.